Okay, first I'd like to thank ACAP for the invitation to speak. I think as PV progresses and moves forward, it's going to be essential to increase the international collaboration and collaboration among labs. So the University of New South Wales has long been a leader in cell technology, so I think they're also being a leader in trying to put together a large consortium to work together to solve some of the problems. So what I'll talk about today is to give a bit of an overview on QESST. QESST is an engineering research center funded or joint funded by the Department of Energy and the National Science Foundation. Do a very quick overview of some of the highlights and projects, and then talk a little bit about the collaborative projects that we're involved with. So the QESST is what's called an engineering research center. It involves a collaboration of universities, industry, national labs, and others to address a certain problem. These are the universities that are associated with the QESST Engineering Center. It is a 10-year, it's anticipated to be a 10-year funding program, and we are presently in year 3 of that. We just passed our year 3 review in May, which was a big deal. We also have international partners, and the University of New South Wales is one of our international partners and the one we collaborate with the most. A brief look at some of the statistics. We have 5 faculty at ASU whose core mission is on solar, and we also collaborate fairly heavily with faculty from physics, chemistry, material science on various aspects of photovoltaics. We have about 35 to 40 graduate students at ASU associated with the solar power labs, and from QESST we have about 20 core faculty. In our annual report we show that we fund 40 faculty with about 150 graduate students, and for any recent graduates there's a little note down there. So at ASU, we not only have a large solar research program, but ASU has also been very actively involved in installing solar. So over the last 5 years, they've installed roughly 25 megawatts of solar. It's interesting to note that ASU stands for Arizona State University. Arizona, if you see the NREL maps of solar radiation, is right sort of in the nice little red zone. And so installing solar actually allows us to installing solar in high insolation climates allows you to very rapidly reach large fractions of installed solar capacity. So presently there's a 50% on certain days of daytime peak electricity is supplied by PV. This was actually hit in 2012 and for the first time, and since then has continued to be met fairly rapidly. I would note that again, this is I say here peak electricity, but this is of the peak plus baseload electricity. So actually ASU, as a slight technicality, achieves slightly higher of its total fraction of electricity than Germany does. Now, of course, ASU is a single entity. ASU is the largest U.S. research university, and I always lose track of the numbers. I believe at last count there was, there's no one else here from ASU I can ask, 76 undergraduates enrolled at the ASU campus. So at ASU, they have the Solar Power Laboratories. This is a clean room that has about total of 40,000 square feet for university industry collaboration. We have about 6,000 square feet of that. We have a full-size silicon wafer pilot line, 3.5 growth, and extensive characterization facilities. So a lot of the silicon solar cell results you'll see are all fabricated at ASU. And I'll focus a little bit less on the 3.5 growth. I'll mention it in passing. The general mission of QESST, or the general vision of QESST, is to recognize that solar is and has been for a very long time on a very rapid growth rate. So the central question is going to be, is the solar going to continue to expand at those type of growth rates, and what are the barriers to doing so? So the central mission of QESST is to ensure that the technology is such that we can achieve the continued growth rates. Now, of course, if you look at other semiconductor technologies, then some of the most famous rapid growth rates are something like Moore's law for transistors. So in essence, what we did when we were doing the QESST program was, is there a Moore's law for analog for PV? And if so, what do we need to work on in order to ensure that PV retains on the very rapid growth rates? So the central, won't go through the details, but the central thing is that in order to look at the Moore's law analog, thickness and or concentration is the analog to gate length for a transistor. And what we're really looking to do is to increase the amount of power or energy produced per material volume. So this translates into the specific goals as shown here. So we're trying to increase efficiency on commercial solar cells. And so really the mission of QESST is to have an impact on technologies that might be, realizable in 10 years. In addition to that, have a focus on sustainability and also look at module approaches. What can you put into what can you integrate into the module that will help address the goals of QESST, either by higher efficiency, higher reliability, net higher power output, so on and so forth. And the final bullet point should probably be one at the top. I note that Paul, in his previous talk and in a lot of talks, you often talk about what are ways to reduce soft costs. I believe that one of the best ways to reduce soft costs is to look at outreach and training. This allows people to understand what's involved in the technology, brings the technology to greater public awareness. So if we actually really want to have a technology that is economically viable and large scale, it is absolutely essential that the public is committed to that. So as part of that, also as Andy said, we are very heavily engaged in outreach and education activities across the whole board, everything from middle school students all the way to the general public. Now, it must be a US thing, since Paul had sort of a graphic representation too, to make complicated, slightly incomprehensible charts on what you actually do. So this is a graphic that is mandated for us by our funding organizations. So I will highlight a couple of features on it. So the main features of this is that we have a fundamentals, we have a set of activities focused on technology, and a set of activities focused on implementation, either commercial implementation or looking at other types of barriers that could potentially be in implementation. What I'm going to focus on is primarily on the solar cell technology here. And there are two major sets of activity. One is high efficiency silicon solar cells, and the other one is tandem solar cells. A lot of our tandem work is focused on silicon-based tandems. I would note that we also have industrial partners, and we do work on conventional tandem devices. And I would also note that Soitec and Fraunhofer recently announced a 46.0%, and that was measured by two laboratories, both Fraunhofer and ACE, and it was announced, I think, 2 or 3 days ago, or maybe losing track of time with the dateline. It was announced within the last few days. So, but most of our tandem activities, because tandem is a commercially viable technology, is done with industry partnerships. The research is very heavy on silicon and tandems, with the focus on tandems on being what can you integrate with what can you integrate with silicon to achieve a higher efficiency. Okay, so what I'm going to do now is give you a very rapid and largely without explanation overview of some of the non-silicon work that we're involved in. And I'll be around for the next couple of days if you have any questions on it. So one of the sets of activities that we work on is gallium nitride and indium gallium nitride solar cells. Gallium nitride and indium gallium nitride is the semiconductor that is most produced after silicon. Its costs have come down very, very rapidly. If you want to buy a epi-ready wafer, sapphire is now actually cheaper than silicon for a larger area. So there are a couple of challenges in applying the white LED materials to solar, including material quality and band gaps. We've managed to demonstrate ways to overcome both the doping issues and many of the material quality issues. On 3.5, I mentioned that the silicon tandems are a very large focus of work. One of the areas is how to integrate 3.5 onto tandem nanostructures. So, for example, looking at how to put on gallium indium phosphide on silicon nanowires. We have a large focus on silicon and silicon-based tandems. However, there is also an effort on thin film. Also, again, keeping with the QESST mission to achieve greater than 20% efficiency. So a key result here is that they've looked at some materials for SIGS tandems and have actually achieved the highest voltage for a high band gap SIGS device out there. Another interesting material, which can also potentially be integrated with silicon, is the dilute nitride materials. So a challenge in the dilute nitride materials is that they've generally had a higher recombination losses. By designing quantum wells and looking at ensuring that the transport out of those quantum wells is efficient, we've managed and this is a University of Houston result, managed to show a open circuit voltage for dilute nitride solar cells that approach the radiative limit. I also previously mentioned that sustainability is a major focus. So there's a very broad range of sustainability efforts focused on the economic sustainability, the environmental sustainability, and also how solar plays into the overall social environment. What I'll do next is, from the sort of very rapid overview of some of the highlights and projects, is focus on some of the silicon activities. So I mentioned that there's a silicon pilot line. It does a baseline for standard screen print, full industrial size. But what we have also done is to ensure that the results, or the system, an implementation system in which we can readily collaborate with others in the results. So this is a web-based system for sharing results where all the runs and all the data is available to anybody anywhere in the world. So they can ask us to process, or they can send somebody to process, and they can view the results the same way that we view the results. A final, this is a little out of sequence. A final area that we've also started to get into is not just looking at photovoltaic devices, but also combinations between photovoltaics and CSP devices. So this is a high temperature indium gallium nitride solar cell that is directly integrated in with a CSP device. So the goal is to increase the efficiency both of CSP and also compared to what you would expect just out of a conventional solar photovoltaic device. And of course, a key advantage is that the electricity coming out of this, some fraction of it is dispatchable. So it gives you a little bit of an idea of the capabilities. There is a wide range of projects which we collaborate with on ACAP. And I won't go through all of them. I'll probably mention very briefly some of the HIT solar cell collaborations. We have a key focus of QESST is to examine ways in which we can increase the efficiency of a silicon solar cell. So the standard efficiency limit of a silicon solar cell is well known to be near 29%. We are looking at ways that we can increase in a realistic commercial device how to get above 29%. So this is a well-known plot by Martin and Patrick Campbell. So one of the approaches is to discard the horizon light, which is generally not captured by a solar cell anyway. If you discard the horizon light, then étendue considerations mean that you can actually go to a thinner and a higher efficiency device. In order to realize this, you need to, first of all, be able to match the thermodynamic potential or the detail balance potential of a silicon solar cell. If you're going thin, you need extraordinary levels of surface passivation, less than 1 centimeter a second, and you also need extraordinary levels of light trapping. So with these, if you can realize these three issues, you can actually get a single junction silicon solar cell with a efficiency greater than 40%. So the first one of those three things that you need is to get the VOC close to the thermodynamic limit. And what we are talking about here in order to do that is a carrier selective contact solar cell. A very brief view of the carrier selective contact is that it extracts at the quasi-Fermi levels rather than at the Fermi level the way a p-n junction does, and therefore lets you get to a higher voltage. A conventional HIT cell is a relatively good implementation of a carrier selective contact solar cell. It does have multiple non-idealities, including high absorption in the amorphous silicon, low conductivity of the amorphous silicon. So a project that we collaborate with UNSW on is to examine candidate materials for a carrier selective contact solar cell. The baseline that we're working from is a HIT solar cell. We've shown open circuit voltages on a measured device and a measured thin device of 753 millivolts, and we've measured implied open circuit voltage of 760 millivolts. And actually working in collaboration with UNSW, with Allison, we've shown over 20% efficiency on initial structures out of these right here. A way to get to a higher efficiency out of the HIT cells is to look to replace the amorphous silicon with other materials. We've looked at rapid screening approaches. Certainly you don't want to spend the amount of time that was spent optimizing the original HIT cell in developing material and seeing if it works. So we've developed some approaches that allow you to do a rapid screening for the suitability of carrier selective contact materials. Multiple of these materials have shown an experimental VOC of over 700 millivolts. The highest has been a gallium phosphide-based device, which showed 720 millivolts using a low-temperature growth process. And actually, one of the key collaborations we've had with UNSW has been on the modeling of these devices, trying to understand what is the key factors that influence the efficiency and voltage out of these devices. The second one of those three necessities for achieving a very high efficiency silicon solar cell. I actually should say the second one was actually a surface recombination of less than 1 centimeter a second. Using the carrier selective contacts, we've actually experimentally shown measured full silicon devices with contacts at an effective surface recombination velocity less than 1 centimeter a second. So the final aspect is how are we going to do a light trapping on a commercial silicon solar cell. And so we've looked at silicon nanosphere lithography. And so this right here, basically what we do is we spin silicon nanospheres onto the top of a silicon wafer, and then we can get a very wide range of surface structures depending on how we process it. One of our key innovations in this has been to adjust the solvents in silicon nanosphere lithography in order to allow more than 95% coverage on full-size wafers. So you can see this right here is a 4-inch wafer, and that we've managed to achieve full coverage on. What is probably the most promising nanosphere approach is that the nanopillars, and we've been able to model and look at some measurements that show a very high fraction absorbed light even in 2-micron devices. These right here is a experimentally fabricated nanopillar on a 4-inch wafer, and there was no fancy equipment in this. We use a regular fume hood, no environmental controls, nothing to make these nanopillars. Okay, I think I'll leave it there. Summary, we are very interested and feel that international and local collaboration is absolutely essential in order for photovoltaics to continue its rapid progression rate. So we've very much enjoyed and feel that there's been a very good set of research outcomes collaborating with ACAP, and I think that's it.
Thank you, Christiana. So, one quick question. Sort of negative time question, I think. Sorry.
So, Christiana, how does ASU fund 25 megawatts of PV at its campuses? I mean, it's not an easy thing to fund, right? So, have you got PPAs in place?
There are PPAs in place. I would note that at least as a data point, the installation cost in Phoenix is we put it on our house, so I have the numbers, is about $3 a watt for over 20% efficient modules installed, full system, everything. So at those prices, given the solar radiation in Phoenix, with no subsidies, no nothing, solar is competitive, is grid competitive with basically at the present time. That would account for the strong reaction to Arizona utilities to photovoltaics, but that's...
But you don't own and operate the plant yourselves, yes?
No, we do not.
Okay, I'm going to call the stop there because it's not really in our scope. So take that one offline, but thanks Christiana once again.